So on my end, I'm Trip Bird. I am a leader of our strategic application engineering team here at Markforged. Been with Markforged for several years and coming from a background of manufacturing, mostly in process optimization and composites. But a lot of what happens in the manufacturing world is directly impacted by some of the current advances in additive technology. And a lot of the tools that are complementary to that exist in the software realm, where this new method of manufacturing needs new methods of part validation and part management throughout the process. So I'm happy to be joined by Olivier here.
Hi everyone, so my name is Olivier Guettard. I'm the business development engineer for additive manufacturing at Extreme Engineering. So my role is essentially to connect with the AM industry to understand what are the challenges, what are the opportunities for simulation to help and to solve those challenges. So I'm working very deeply with the product management and product development team so that we can work on the roadmap, defining what are the different, the next steps of our simulation and how we can help the customers with simulation. So I'm at Extreme for 4 years now, and before that I've been working for 4 years in the aerospace industry. And I'm very glad to be here with you today.
All right, thank you. So while we launch into this, a quick background about Markforged. So Markforged has been around for half a dozen years and is a growing and industry leader in the world of industrial 3D printing. We produce an ecosystem of hardware, software, and materials that are designed to work seamlessly together to allow engineers to quickly and easily produce functional and accurate parts that can be ready to use straight off the machine. Now, growing globally, we've got tens of thousands of machines scaled around the world, all managed by some unique cloud software tools called Eiger that allow for up-to-the-minute connectivity with fleets distributed regionally, allowing for virtual inventory management and distributed printing as necessary. So our current portfolio stack looks something like this, where a range of industrial 3D printers differentiated primarily by the ability to 3D print continuous filaments or continuous fibers. So this differs in functionality and performance from most fiber-filled 3D printing materials, where traditionally you have a base plastic mixed with a short length chopped fiber that dramatically increases the strength and dimensional accuracy of a component. However, it's still limited by the short chop length of the fiber. Markforged pioneered the invention of continuous printing, where a print head extrudes a second material mixed with a complementary binder that allows it to print fully structural, fully strong parts that in many cases can exceed the strength of aluminum due to the properties of continuous strength fiber. This allows functional parts straight off the machine, coupled with an enterprise software solution that allows for easy management of builds, different reinforcement strategies, as well as print fleet management across the entire ecosystem within your installation. Multiple users collaborating together to provide functional parts around the world. All this coupled with a range of engineering materials to provide functional strength. In the composites world, we've got materials for higher strength, for flame resistance, for different surface properties, but then coupled with the ability to print continuous fibers such as Kevlar, fiberglass, or carbon fiber allows you to really tailor the performance of a part for a specific application. More recently, the ability to 3D print metal in the Markforged ecosystem has become available. This is based on the existing MIM industry, where now rather than shooting MIM powders into a mold, we're extruding them out of a nozzle, building up a 3D shape layer by layer. Then through secondary steps of debinding and sintering allows you to get a fully functional metal part out of a system in a matter of, a minimum of 2 days, which compared to traditional methods is often orders of magnitudes better in delivery time and price. So in the world of 3D printing, obviously prototyping is extraordinarily popular, extraordinarily high value compared to traditional methods. This is where the fast delivery time and the ability to mock up and iterate development very quickly allows for faster time to market, improve product design, improve functionality all around. But if you look at the overall revenue of the Fortune 500 manufacturing companies, the actual spend in the prototyping world is, pennies compared to their overall core competency. So the addressable opportunity is a bit limited compared to their core business. Now, growing rapidly through in part way, the adoption of Markforged, tooling is becoming extraordinarily popular. This opens up a much wider scope of addressable opportunity compared to the overall bottom line of a business, has still extraordinarily high ROI due to the low part counts and complexity and low production volumes necessary for specific part tooling. It does, however, move a little bit more up the risk chain where you've got now part touching details, you've got things that are impacting the quality of a part that a customer might see. So as far as the de-risking that's necessary to push this into more high value applications, sometimes other steps are necessary. And finally, the ideal end state is the ability to 3D print end parts. This unfortunately has seen limited implementation. However, it's growing rapidly. Some of the areas of advancement are focusing on the geometric complexity allowed by additive, or the ability to drastically streamline supply chains by being able to design centrally, send files around the world, and then print locally on demand. This is greatly reducing carrying costs in warehouses where one part on the shelf and an infinite number in a virtual library allows for on-demand replacement, but then the ability to restock without having to rely on global shipping times or third-party vendors. So the ROI here is huge. However, the comparison against traditional methods, the cost per part compared to injection molding or something is not valid today. However, the other benefits in the worlds of logistics optimization certainly drive more value. The risk here is quite high, though. Oftentimes with additive manufacturing, we're dealing with a new material, a new design, and now a new method of making this part. So we're changing a lot of variables at once. Anything that we can do to de-risk that really drives value to the customer and allows them to better access that largest chunk of a company's revenue. Most manufacturing companies exist to make end-use parts. The closer additive manufacturing can get to that core competency, the more value we can potentially drive to our customers. And that's really what is the impetus behind Markforged. We're not making prototyping machines. We're not making R&D experiments. We're making tools for the factory floor. So what we want to talk about today is how do we de-risk some of these things that allow the unlocking of more addressable opportunity for these customers. So with the complex amount of variables involved in the printing process, we've got fiber choices, we've got laminate schedules, we've got environment around the printer, material choices for the base plastics, the design. There's a lot of things that are changing. However, ROI, the financial drivers behind making these parts, predictability and repeatability become core as we start to push these functional components into higher risk areas. Software is becoming an extraordinarily powerful tool to help manage these variables and begin to predict the performance of these parts before they hit these critical applications. So a little graphic here just to go into further detail about the properties that continuous fiber can deliver. So the composites industry, well understood, been around for in the world of carbon fiber and Kevlar and things like that for decades, and has proven itself time and time again in the worlds of aerospace or other highly critical applications. Now, driving that down, carbon fiber here you can see still has extraordinary material properties where some other materials compared to Kevlar or fiberglass, you can allow yourself to tailor a design for flexibility, impact absorption, high stiffness, things like that. And in many cases, often exceeding the strength of aluminum, which for most tooling and fixturing applications is a very common material due to the availability and use of machining, things like that. So by driving the ability to print carbon fiber in these functional applications continues to unlock more value for our customers. Which brings us to Danfoss. So Danfoss is a worldwide industrial manufacturer. They make a wide variety of components for different machine centers and different applications. However, working with Danfoss Power Solutions in the US, we've developed a great relationship. They're popular Markforged users in the world of tooling and fixturing. However, in their business, they have a high mix of relatively low volume castings and housings for all of these pumps and things that go throughout their process. They very much like to use Markforged in all of these areas to improve tooling in their part creation stream. The challenge is that much of this tooling is lift assist. You're lifting these heavy cast metal components and moving them from machine center to machine center for different drilling and milling operations as they go down the line. These lifting applications are higher value than a standard drilling fixture or nest or something. However, now that we've got lifted metal, worker safety becomes critical. So right now, with their application for 3D printing, they found that it meets the technical requirements and the financial metrics necessary for a lot of the typical shop floor things. However, the areas that they'd really like to apply this technology is limited by risk. Up until now, they've been limited in their ability to adopt additive in other areas of their business due to the extensive testing required or validation steps necessary to print a prototype, destructively test it to ensure it meets load, then roll it out for one production application. When you're dealing with a very high mix of parts, that becomes costly and very drawn out on the timeline, so the benefits of additive are eroded away. This is where Danfoss, being a joint customer of both Markforged and MSC, drove a relationship here where they've identified industry partners that have the tools necessary to solve this problem for them. So the challenge in this case was to validate using software tools the performance of 3D printed composite parts to ensure that they could meet the safety and repeatability requirements necessary to replace much of their machined aluminum tooling on the factory floor. So by de-risking this application, they were able to apply it in certain areas that otherwise had been prohibitive to do. It allows for increased safety, new designs for increased ergonomics or lighter weight for increased handling, and still delivering all of the benefits that additive typically provides, such as time to market, faster iteration, no external PO process or waiting for external sources. So on the Markforged side, a quick intro of how we go about this process, looking at this lifting sling. So in this case, it's a very function-directed design. If you compare the shape of the existing aluminum version versus the printed composite version, we've made a few tweaks that are visually apparent, however, functionally produce no difference in the performance of the part. It's made it lighter, it's made it easier to grab, it's taken a multi-part assembly and reduced it down to one piece, and allowed for better tailoring of the fiber pathing to be in line with the load. So looking internally here, and I'll go through the Eiger view in a second to do it live, but you can see that while you've sliced your part for 3D printing and Markforged, you then have the ability to go in and reinforce internal features with particular laminates to strengthen certain areas or provide robustness for different loading conditions. So we'll go in and show how this works. Give me a minute. So Eiger is our software, typically cloud-based. Most of our users are comfortable with that, now being ISO 27001 certified. Our customer IP is extraordinarily important to us, and their security with their existing libraries. So this is the workflow in Eiger. Part is imported. You have the ability to orient as necessary. It'll snap to certain features to be able to present the best way to print. In here with our printers, you have the ability to select not only the base material, so I can choose anything in the Markforged ecosystem. So Onyx, which is our short chopped fiber reinforced modified nylon 6, or I can choose any other material that is in the Markforged ecosystem, Onyx FR, if this is a flame resistant application, or even the tool steels if you wanted to transition this to the Metal X rather than the industrial series. Then on the fiber side, the ability to print Kevlar, carbon fiber, high temp, high strength fiberglass, all of these things that can be chosen for different properties desired of the part. Once the global settings are determined, the ability to go in and do the actual composites engineering is possible. So in the internal view, you can get a 3D fly-through version of the internals of the part. So rendered here, you can see we've got 5 laminate schedules, or laminate stacks of fiber, where we're reinforcing the outer planes. We're running concentric fiber between the load-bearing top ring and the pins at the bottom of the component that actually nest against the metal casting. And then going in layer by layer, you can actually engineer the performance of your part here to produce certain properties. So in this case here, you can see we have concentric fiber routing around the lifting ring and running all the way down the pins here that connect the load to the bottom piece, and then allowing for any sort of laminate schedule you need. You can go in and change fiber orientation, fiber rotation, things like that that are necessary to improve properties in certain bias. So your 90-degree fiber and then an isotropic laminate stack that helps give strength in all dimensions. Then down here, the ability to reinforce through holes, things like that for strength in preventing any kind of point load through the walls of the part. And then for the areas that don't require reinforcement, the ability to run just our base plastics material in a honeycomb, very lightweight, however, still allows us to put the fibers at the outer extent of the part to get the section modulus as high as we need to prevent deflection in some of the other directions. So extraordinarily powerful here. Once engineered, then the ability to go in, and this is where the new functionality comes in, to export this geometry into a format that can be digested by simulation software. It's much different than just exporting the geometry of the part, showing walls and infill, because we also need to understand the vectors of this fiber position. It's not only where the fiber is, but which direction is it pointing that really matters. And doing that layer by layer by layer throughout the whole part, and then exporting that into a format that can be ingested by our software tools is really where the innovation is on this platform. So going from here, I'll allow Olivier to show the next steps once a sliced and reinforced file is sent out for export.
Thank you, Trip. Let me share my screen. So you should hear me and you should see my screen. So who we are? Extreme is essentially a team of passionate material and process experts. So we are a small company, around 80 people, essentially PhDs and material engineers, which was created about 70 years ago. And we have the 2 main headquarters located in Brussels and Luxembourg, but we have offices in many places, including in the US, of course. So at Extreme, we developed 2 different softwares. The first one is the material and process modeling platform called Digimat, which is more specifically dedicated to composite materials, so any multi-phase material. The second software is Material Center, and is a material lifecycle management platform that allows you to store, to track any material data in a unique centralized platform. So that is specifically very powerful for additive manufacturing, where you could imagine to store any kind of data related to your printing, from the printer serial number, from the material batch that you have been using, from the build with how many parts you have been printed, up to the test data that were performed on the same build. Okay. Since 2012, we belong to MSC Software, which owns a very large portfolio of CAE softwares like Nastran, Mark, Apex, or Simifact. And 3 years ago, MSC has been acquired by Hexagon, a leader in inspection hardware and software, So for instance, Leica, Romer, Icon, they all belong to Hexagon. So the idea is that before acquiring MSc, Hexagon activities were essentially focused on the end of the manufacturing chain. So they were able to conclude whether the part that you produce was compliant or not, thanks to the different metrology systems. But they were not specifically able to tell you what needed to be changed in the process or in the design. So by acquiring MSc, Hexagon desires to kind of empower a very strong digital continuity with both design and methodology tools. So combining the real world with the digital world. So that's just to give you a very broad overview of who we are and what we develop. Now, if there is one slide to remember on Digimat, I think it's this one. So with our multi-skill technology, Digimat bridges the gap between the manufacturing and the part performance. Okay. So if you think about continuous fibers, for instance, the pathing, the layup strategy, they will of course both dramatically impact the material behavior and finally the mechanical performance of the design. And so the idea here is really to deduce the as printed material microstructure from process data, for instance, the build orientation, the tool path, so that we can predict accurately the part performance. And this is actually the same philosophy as what we developed for injection molding 16 years ago, an approach called ICME. So this stands for Integrated Computational Materials Engineering. So the solution that we propose for additive manufacturing in partnership with Markforged is based on essentially three key building blocks. So we have material engineering, process simulation, and part performance, but it can be extended with Hexagon and MSc products for topology optimization and part inspection. So here during this webinar, we will essentially focus on the material engineering and the part performance side. So in order to perform structural analysis of Markforged design, there are essentially two key ingredients that we add to a finite element model. First, we are finalizing an interface between Eiger and Digimat that allows us to have access to the filament and the fiber pathing. So that's really the first key aspect. The second is that we calibrated a Digimat material model based on experimental testing, and the combination of the manufacturing data and the material model that is toolpath dependent will allow us to predict the as manufactured part performance. So of course, the very first step is to create a finite element model. So you need to mesh your design, you need to apply the boundary conditions, the loading that will reproduce the in-service conditions. And the good news here is that we are interfaced with most FEA softwares on the market. So of course, MSc, Nastran or Mark, but also Abacus, LS Dyna, ANSYS or SAMSEF. Okay, so these are really the key steps that we propose to validate and optimize the design performance of the Markforged printed parts. Now we will deep a bit more into the details of each of those different steps. So the first one is about the toolpath. So the idea here is that thanks to our partnership with Markforged, you will be able to export, as was explained by Trip, the toolpath from Eiger, import it in Digimat, load it, and map the filament material. So is that onyx, is that composite material, and its orientation onto the structural mesh. So for that, we have a specific workflow that allows us from a given toolpath to map this information on the structural mesh. So somehow we need a simulation to be aware of the toolpath, toolpath orientation. So let's take an example, very simple, of a dumbbell with unidirectional paths. What we want to do is to be able to retrieve what is the orientation of the filament with the orientation X, for instance. Let's start with this one. So these are the value of the orientation tensor that we are showing here. And the field here will tell you how much aligned my filament is with respect to the X direction. One means that I am perfectly aligned, which makes sense everywhere in the part. except on the two boundaries where we see a blue value, meaning that we are exactly orthogonal to the x direction. Okay. If I did the inverse, so if I was displaying here A22, then I would see everywhere blue value except here where it would be in red. Now let's have a look at 45-degree angle. So here again, we will see the effect of the contour, and because the mesh is fine enough to capture that contour, we can see it captured here. So again, we will find that the contour is very well aligned with the x direction. Again, orthogonal on the two extremities, and then everywhere in the infill, because of the 45-degree pattern, we will find a 0.5 value. So this is exactly how we manage to have that connection between the toolpath and between the structural analysis. The second step requires to perform different mechanical testing on the onyx, but also on the continuous fibers, and to calibrate the Digimat material model by reverse engineering the test data. So the material that we need must be able to reproduce the different characteristic directions that are defined by the toolpath, and that will drive the typical orthotropic material behavior that we can see here. So if we consider a unidirectional toolpath for this example, made of onyx material, so we have the different layers here and different beads, we can see that there is a very distinct behavior which is obtained in the direction of the filament, transverse in the direction or in the printing plane, or along the building direction. Okay, and so with our different models, we are able to reproduce this kind of orthotropic material behavior, and the onyx and the composite have been calibrated based on experimental data, and they are also toolpath dependent. So when we started investigating the Danfoss tooling design, we had the pleasure to find an additional challenge. So what you see here, it was explained by Tripp. So it's the relatively systematic use of triangular infill. So while it makes perfect sense to gain material, so to also gain weight and printing time, it is an important aspect, of course, that needs to be integrated into the simulation workflow, because it will, of course, affect the material behavior and the part performance in the end. So to this end, we are using Digimat FE, one of our different tools, to create first the unit cell of the infill. So this is the symmetric unit cell of the triangular infill that we reproduce here, just by defining an array of different nodes and by clicking to create the associated junctions, so the different struts, if you want. So once that geometry, that can be any kind of geometry, is reproduced in Digimat, it will almost automatically mesh the geometry, assign the right material behavior, so onyx here, the boundary condition and the loadings. And so we can run that analysis, post-process the different results, and export the equivalent material behavior to the finite element analysis, so that we don't have to mesh very finely this kind of infill at the level of the part, of course. So in other words, we have really developed here and applied a multi-scale workflow that allows us to take into consideration the as printed material microstructure at the finite element analysis level. So at the end of this workflow, the finite element results have been validated against the experimental test. So basically two different parts have been tested, one made of onyx only, and the other one with continuous fibers, and they have been tested in the tensile bench that you can see here. Okay, so as you can see, the right failure location was found by the simulation that can be seen here from the experimental results, and we also have a very good agreement between the test data in gray and the Digimat results in blue for the onyx and for the composite material. And so only adding a couple of additional layers of composite here was able to almost double the stiffness of the material. And in total, the part was able to sustain more than 7,000 Newton. So to summarize the solution that Digimat is offering for Markforged designs, we need to access the toolpath data from Eiger. And that is really thanks to our partnership with Markforged. We have that connection to feed critical process information from Eiger to Digimat. you need to access validated material models. And so since our previous release yet, we already had calibrated the onyx and the continuous carbon fibers models. We need the part stiffness and failure to be dependent on the toolpath. And for that, you have seen from the workflow that we need to import the toolpath file in Digimat, and then to map the toolpath from the STL to the structural mesh. And that will be illustrated during the live demo just afterwards. And finally, of course, we need to set up and to run the finite element analysis. And for that, Digimat RP is coupled to most FEA solvers on the market. Again, MSc Mark, Nastron, but also Abacus, ANSYS, or LS-DYNE. So it's time for the demo. So I will switch to the Digimat platform. And you can see here that we have different tools and solution. The one that I will be selecting here is Digimat RP. So again, keep in mind that Digimat RP is not a finite element solver, meaning that the very first step is that we consider that you have already introduced here your input deck. So you have already a mesh that is existing on the part that can be seen here. You have already the boundary conditions, the loading that are assigned and so on. Okay. From here, we will essentially add the two ingredients that I mentioned before, meaning the Digimat material model and the toolpath data. So let's start with the tooling from Danfoss here as a first example. And we will first see a workflow where we only use the onyx, and then I will illustrate another workflow with composite material as well. So the very first step here is to select what manufacturing we are interested with. So in this case, it will be fused filament fabrication for the onyx material. I will select a fiber reinforced polymer as the onyx is carbon filled. And then I can select the file to be loaded. So here I'm adding the Digimat material model to the Digimat LP interface. And once this is done, I will define the different manufacturing data. So here I have the choice between selecting a file that has been already mapped or doing the mapping within Digimat LP. So for the sake of the demonstration, this is what I will do. So here we need to select two different files. First, the STL file. So that's nothing more than a surface mesh. And the second is the file that is coming from Eiger, so the toolpath data. So I will load those data here in the interface. And once this is done, I will be able to review the toolpath. So just to make sure, for instance, that I selected the right one. So that it can be illustrated here. So if I zoom in, you will see first a couple of dense layers of onyx. And then very quickly, you will see the famous triangular infill here. Okay. And of course, I can move on progressively. So at this stage, I have two different meshes. On the left, you have the structural mesh. And on the right, you have the manufacturing mesh, so the STL file. And of course, we need to do that transfer, that mapping of the toolpath into the structural mesh. So this is what we do here. So it will open a new window where we will see first if the two meshes are superimposed or not. In this case, it is they are superimposed. So you can see in red the STL file with the Danfoss logo, and here in gray you have the finite element mesh that is described. So they are perfectly aligned, meaning that I don't need to do any additional step of superimposition, and so I can basically start the mapping procedure. So that will take 1 or 2 minutes. So while this is running, I will initiate the other workflow on the dumbbell where we'll also associate continuous fibers. So we start our same workflow, meaning that I will load my input deck. So this is an input deck with MSc Mark in this case. Again, you can see the mesh that is displayed here. We have fixed one of the extremity and the displacement is applied on the other extremity. So very basic. Now, the very difference with the previous one is that we have predefined element set that will allow us to assign the right material on the right elements. So here we'll see, in this case, the onyx, that is essentially the outer shell of the dumbbell. And then in the core, if I pass my mouse on the carbon fibers element set, you will see that all the core is made of carbon fibers. So that's just a choice of myself, just for the purpose of the demo here. And I will need to assign the material and the manufacturing data to both those element sets. So let's start with the onyx again. So this time I will select continuous fiber fabrication because we have composites in the design. First with the onyx, so this is with the short fibers reinforcement. I will again load the onyx material card. And then I will load the manufacturing data. And in this case, it's the already mapped data that I will integrate. So I can load this and see that here, essentially, I've been using a unidirectional toolpath. So that's why we have one value almost everywhere on the design. Then I can review the different settings, potentially change some of them before I can see that I have the green check here, meaning that for the onyx, we are ready to go. Now I need to do the same for the carbon fibers. So that means that I need again to select continuous fiber fabrication. To select this time the continuous fiber reinforced polymer, I will select the composite grade this time, so the associated material model, and again define the same material data that will define the material and its orientation everywhere in the part. And if I click on review, again, I can define some of the changes related to failure and other kind of damage parameters. But basically at this stage, I have the green check everywhere. So I can just click on submit the job, and then I can start the analysis. This will launch a coupled simulation between Digimat and the finite element host that will run in the background. Okay. And then once the simulation is over, I will be able to post-process the results in the finite element host. So going back to the mapping procedure, you can see that the mapping is over now. And similarly, as the different examples I shared on the dumbbell, we can see that if I'm selecting the A22 component, I will see to what extent the filaments are aligned with the Y direction here. And so, of course, on the contour, we are perfectly aligned, orthogonal in this area. And here we have very likely a 45-degree infill. So that's we see the green value of 0.5. And once it is done, again, for this onyx design, I can just review the different settings and again, run the simulation. So that's it for the different simulation workflow. I will go back to my presentation. So in summary, what has been performed as a work with Markforged here is first that we have characterized the onyx and the carbon fibers materials. We have a capability to import the fiber pathing and first export it from Eiger, of course, defined under the form of vector data. We, of course, need to simulate the different in-service loading conditions with the help of the finite element model, and then we can predict the performance by adding the toolpath data. So that was how we were able to evaluate the Danfoss design. So we can see here that in the case of Danfoss, we have met the different functional requirements. We have met the different ergonomic requirements thanks to additive manufacturing and to the Markforged technology. If we can get rid of any testing to failure, it means that basically we can have a faster time to delivery. We can also expect cost savings up to 10 times. And of course, we have shown here that the printed part was able to survive 7,000 Newton in the loaded testing. So that is great, but if that work was specific to Danfoss, it will not really help the industry. So what we are proposing here, thanks to our partnership and thanks to the Digimat platform, is that we will basically have access to the same material model. So those material models are embedded in the Digimat MX database for the onyx and for the composite, at the moment for the carbon fibers only. And you will also have the ability to export the toolpath data from Eiger so that you can perform your different simulation to validate, optimize, compare the different toolpath strategies that you want to investigate. I guess with that, we completed the presentation part of this webinar. And it's now time for questions.
All right, thank you, Olivier. So a reminder, you can enter questions in the chat and we'll get to them as many as we can. So question of what sort of data file is necessary to analyze the geometry and strength? STL, IGES, etc. So in this case, the STL of the geometry to be analyzed is necessary to import into Eiger for slicing, but also to import into the Digimap platform for meshing and overlay. Then the material card would be required. This is the properties for the carbon fiber as well as the onyx. This is existing in the Digimap material library right now and is something that can be found in our material spec sheets as well. So those combined give you the raw inputs. Then the vector file showing material position and orientation within your part is the third component that's necessary. That is an export from Eiger in a JSON file format, but showing position and orientation. It differs slightly from the Markforged MFP file, which is our build file that is used to send the builds to the printer. The build file captures the movement of the head to put the fiber where it needs to go, and the JSON file records actually where the fiber ends up. Part of the Markforged secret sauce is how we move the print head to get material where it needs to go. That is not the same as where the material ends up. So the two different file formats there are necessary for the different properties required. That export functionality will be available in an upcoming release of Enterprise Eiger. So if it's something you're interested in, reach out to your Markforged contact and we can discuss. Expect towards the end of the quarter for availability. Right. Let's see what else here. Olivier, there are a couple questions that are specific to MSC. If you'd like to tackle those ones. Is it possible to run an Abacus model on a remote host, or must it be a local machine with both Abacus and Digimap?
That's a good point. So the point is we are able to, so when you're submitting the job from Digimap RP, as I have shown, you have two options, either to run the analysis locally, meaning on your own computer, and assuming, of course, you have, in this case, Abacus installed on the same computer as Digimat. The other option is to create the input deck, so export it if you want, and then export that input deck onto the remote cluster and run the analysis there. So that's something that you can perform.
Got it. And then another MSc question: is any continuous fiber FFF process specific physics captured by the MSc simulation tools?
So here, what we are adding on the part performance side is a specific material model that is modeling the behavior of the continuous fiber. So that is typically what I've shown in the live demo with the dumbbell, with all the core that was made of this continuous fiber. So with that, we are able to tackle, let's say, static type of performances. We also do have another module tackling process simulation. So more with the idea of investigating what is the thermal history while you're printing the part, what is the level of displacement that you might get at the end of the simulation and so on. This one is limited to the onyx material at this point, not yet to the composite material.
Great, thanks. And then on the Markforged side, at the moment, the export file does not currently capture the print specs throughout the build as far as nozzle temperature and position and orientation. Those type of tools necessary for virtual part validation and ensuring uniformity across builds. That's something that is on our roadmap, but not being launched at this time. A question: why don't we have the entire materials database in Digimat? That is our goal. However, for this exercise, carbon fiber and onyx were far and away the two most highly requested materials. So it's just a matter of time as we go through and test robust sample sets of coupons to populate our other material properties for the additional fibers and plastics. So if there's a particular demand or interest that you have, feel free to flag it to Markforged and we will get to testing. Tutorials. Olivia, are there any good Digimat tutorials out there?
There are, yes. So we can, the easiest way, I guess, is to contact me offline, and then we can direct the customer to those kind of tutorials. Yes, sure.
Right. A question about this FEA process applying to metals as well. I assume that means for the Metal X. And with Markforged right now, it is limited to composites. However, metal is absolutely on the roadmap. There are some added challenges there because the printing positional data from the printhead and the slicing does not relate directly to the, or not relate linearly to the end geometry of your part, given the shrink and deformation in the sintering side. So there's going to be an added complexity there of coupling the print pathing with the sinter deformation models that we built into our Eiger. So it's something that'll be coming, but isn't available quite yet. Let's see. Will it be possible in the future update version to define fiber orientation independently of the part geometry, similar to a tailored fiber placement approach? Interesting. So in this case, you can absolutely, in Eiger today, you can tailor your fiber placement almost infinitely. You can go layer by layer. So depending on the thickness of your part, it's either 100, or the thickness of your fiber slice, it's either 100 or 125 microns per layer. So every layer of that step, you have the ability to determine your reinforcement schedule as far as orientation of fiber around the perimeter of any internal or exterior surfaces, as well as the orientation of that stack of fiber in there. If you imagine it as running string around the perimeter, and then the ability to place effectively unidirectional fiber across the entire plane, you have the ability to tailor that fiber placement in any orientation for each layer. So that allows you to define laminate stacks in any sort of repeating fashion that you'd like, and then scale those across the part. There is a discussion in the future to be able to have even more control over each layer, saying I need fiber in that corner of the layer, but not in that corner. That is something we're working on. But at the moment, for layer by layer approach, you have full control over the exact orientation of each strand. Question here, is Markforged able to provide the carbon fiber as well as onyx? So yes, Markforged makes all of our own materials. So onyx is our base plastic, which is the modified nylon with a very short length chopped carbon fiber powder. Then the continuous fibers that we offer are a continuous strand pre-pregged with a compatible resin to bond with the base nylons. So Markforged provides all of those. The material properties are available in Digimat today, and that's available for the rest of the materials as we continue testing. On the software side, Eiger is free and available for everyone to use. Functionality is limited to Markforged systems because we're the only ones with the ability to print fiber in the way we do and things like that. So you can't export Markforged Eiger files for other devices. However, anyone can make an account, eiger.io on Google Chrome, and you have the ability to import STLs, play around with fiber laminate schedules and placement, get real-time cost estimates and build time estimates, things like that. So it allows you to experiment and validate a business case before you even consider implementing this. Right. using continuous fiber, are you able to help compensate for the non-isotropic properties of FDM? So in this case, continuous fiber is limited to the plane of build, where we're able to lay strands in the plane of the build. So the downside to that is that we cannot build up the Z angle of the component. So performance with fiber is extraordinarily high in X and Y. However, the Z strength is still limited to the Z strength of the materials. These properties are imported into Digimat and allow you to predict the performance of your fully built part. A trick that a lot of our customers use that is often even cheaper and easier than trying to path a 3D tool head or something like that on the end of a robot arm for tape laying. In this case, running a bolt through the part dramatically increases that tensile strength in Z. Real cheap, it's off the shelf. And for most of our tooling customers, that's a much simpler approach than it is to try to engineer in 3-axis of build. Right. Can metallic structures be replaced by composite ones in the future? Absolutely. So the target of this webinar was to illustrate how 3D printed composites and Markforged are replacing traditional machined metal structures. From a functional performance point of view, physically they can do it. Now we have the ability to virtually simulate and validate that before we go to print. And as people get more comfortable using our ecosystem and become more familiar with the design constraints and advantages in certain orientations, more and more applications are continually unearthed. Once engineers, especially people on the floor of a factory faced with the problems they see every day, once they couple that understanding of their business challenges with the horsepower provided by Markforged, we're seeing metal being replaced in applications I never would have guessed. It's really powerful to see creative problem solvers out there on the factory floor using these new tools in unique ways. So that brings us about to the end of the end of the hour here. So any questions that we weren't able to do, we can follow up with afterwards. But thank you all very much for joining. I hope it was interesting, and feel free to reach out to contacts at Markforged or MSC if there's any more detail or further communication that we can help with.
Thank you, Trip. Thank you, everyone. I hope that was useful and looking forward for this very exciting journey.
Great. Thank you all. Have a good day.